Okay. Good afternoon, everyone. Welcome. Our speaker today in our seminar is Alberto Hernando. Alberto Hernando got his PhD in the physics department of the University of Barcelona back in 2011, and his PhD advisor was Manuel Barranco, that was here yesterday, and that was a work on helium nanodroplets, quantum physics, and on that aspects. He was for some time as a postdoc in Toulouse, in the University Paul Sabatier, and then he moved to EPFL, the Polytechnical University in Lausanne, where to the Department of Theoretical Physical Chemistry, where he was there a postdoc for 2 years also. After these 2 years, he got a grant from the EPFL to start his own enterprise, which is called Social Thermodynamics Applied Research, and he founded that, and he's been working on that since that time, essentially on problems of human mobility, electoral processes, and that type of thing, while he kept doing some work on research on helium. So it's a pleasure to have him here today, and I think that what he's going to tell us is how what one learns solving Schrodinger equations and doing quantum physics is also useful to look at human mobility problems. Welcome, Alberto.
Thank you. Well, hi. Thank you for the invitation. I want to tell you a story today that is indeed how all the things I learned about computational physics applied to superfluids, how I use them in order to understand human mobility and collective human behavior. And not only that, also how what I learned from collective human behavior, how it was useful to understand a bit better Schrodinger equations as well. So this is both ways in this story, how one field affects the other, and for that reason, you might ask, how is possible? I mean, we know physical systems, and for instance, these fractals that you might find in many nanostructures. Well, how this could be related with human mobility, and how human mobility can be related with that. So I want you to see this in particular. So here, what you see here is actually, probably you recognize the shape. This is Spain, and all the lines that you see here are actually the roads of Spain, starting in Madrid. So these colors, what represent is the probability of finding a random walker starting in Madrid and after a period of time being anywhere else. So this data is taken directly from Google Maps. So computing the isochrones from this starting point in Madrid to any other point in Spain. And you can see that. I mean, it's a fractal, indeed, and very similar to those that we can find with this diffusion aggregation stuff. So it's complex. This diffusion in a road network is complex in one hand because the structure is complex, indeed, because if you consider a walker that can only move in the road system, he will face fractal in order to diffuse. And it's also complex because we are talking about humans that they definitely don't move as particles. So, but indeed, many of the techniques that we are using for physics, for these fractals, indeed they will work for the roads. At least looks like that. And it's not that we Spaniards are weird in how we make the roads, but this is something that you can find almost everywhere in any country. This fractal structure. This is England, starting in London, and this is United States, using 2 points of starting, the West Coast and East Coast. So why is a fractal? That's something we wanted to learn as well. But I can anticipate 2 factors here. One is the geography, indeed. So mountains are fractals, so if you try to circumvallate the mountain at the end, you get a fractal, but it also has to do with how we connect every point in the space. But we will check for that later. Because I want first to talk about superfluids, And why superfluids? Basically, the methods I was using to understand superfluids there, from the microscopic point of view, like diffusion Monte Carlo, in order to define the structure of these systems, but also DFT, that is a more macroscopic view of the system. These two techniques, indeed, they can also apply, or these two philosophies can be also applied when we talk about people, or social physics in general. Indeed, you can use a microscopic description where you describe every human, or you can use a macroscopic one that you describe the world, the society, the groups. And then I will talk again about quantum systems, because indeed when I was working with this population data, in Spain in particular, I figured out a method to solve a Schrodinger equation inspired in the methods we were using there for demographics. But you will see. So first, superfluids. You can find many different systems that they are superfluid. You can find helium, that is the best known because it's the first known superfluid. And you can have the bosonic one, that is helium-4, or the fermionic one, that is helium-3, forming Cooper pairs. And you have in the macro scale as well. It's not only a quantum system in the sense of the scale, small scale, but you can have the bulk of helium that scales quantum behavior to the macro scale. But you can have indeed Bose-condensates, that where you have this rise of vortices and they behave as superfluid gas. That's another example of the system. Or you can even find based on photons and electromagnetic slow photons, these experiments of passing light through the Bose-condensates, that you can talk about interacting photons and superfluid of photons. Or also the polaritons, that has the merit that they work at room temperature. You can also find behavior similar to superfluid. But I will focus in the helium thing because that was my main work on that, and the techniques we were using to describe. First, why helium is a superfluid? So helium is a small atom, so the interaction is really weak between two helium atoms. It's like 5,000 weaker than the interaction between hydrogen, for instance. And since the mass is light, this potential world, compared with the kinetic energy of the localization of the atom, is very similar. So you can hardly have even a dimer of helium atoms. You cannot have a dimer of helium-3 atoms. You can have it for helium-4 atoms. But when you have even more than one, at the end you have the delocalization, the contribution of the kinetic energy to the wall is quite higher compared with the potential energy that keeps the system together. At the end, indeed, you can have finite systems, you can have clusters, you can have droplets actually, but they are really weakly bound. But at the end, transform that you have, like helium is liquid even at 0 temperature. So the question here is if you can talk about superfluidity in a small system, in a droplet. I mean, because we know superfluidity when you have bulk, when you have the macroscopic thing, but it was not clear if you can talk about superfluidity when you have small clusters. But experiments that were measuring the rotation of molecules inside the droplets, at the end you can find that it's almost free rotation. What means that there is no resistance from the liquid to the movement. And that's something very typical from superfluids. You don't have dissipation until a certain velocity, the critical velocity. So that was kind of understood as the proof that indeed helium droplets are also superfluid. And the typical experiment works like that. You have a nozzle, so you expand the fluid, so you form these small droplets. They pass through an oven where you have in gas phase any atom, calcium, any impurity there. So you can control how many atoms you want per droplet. And then you can make a spectroscopy to this particular atom in what is this type of one molecule experiments. You have Avogadro number of droplets, but per droplet you can have 1, 2, 3 only atoms, different species, in order to see how they interact with each other and so on. So how to simulate that? I'm a theoretist, so I wanted to describe these small clusters there. So the first idea was a full microscopic description of the droplet, using, for instance, a quantum Monte Carlo. If you are not used to it, basically you describe the wave function as an ensemble of Walkers. So you transform the Schrodinger equation to imaginary time, so at the end you have a diffusion equation there, right? So if you check the propagator and you imagine that you describe the wave function as this ensemble of particles, of Walkers, at the end you have a first step that is the one of the potential, the potential energy that tells you where to create or where to destroy Walkers. And then you have the part of the kinetic energy that is the diffusion part. So at the end, this microscopic techniques works that you have these Walkers. You can start with any distribution of Walkers, but by killing and by creating new Walkers, at the end it should converge to what is the ground state of the system. And no matter the number of dimensions, you can have here a branch of particles, you should get asymptotically this ground state. So at the end of the day, the wave function is the histogram of all these Walkers when they reach the stationary state. So that would be the microscopic description of this system.
So you decouple the exponential into the exponential?
Yeah, this equation is not solved explicitly like that, but it would be exact if indeed the interval of time is small. But it represents this factor, this Boltzmann factor here at the end, represents the probability of creating or destroying a Walker. So in those places with the probability, the energy is high, the probability is low, so you kill the Walker. In those places where the potential is low, so the probability is high, is where you create new Walkers. And then you diffuse them as random Walkers here, because the kinetic energy at the end, what you have is a Gaussian-like distribution for the movement, so it's a Brownian Walker here.
No, when you say this, I mean the two can not commute, so this is an approximation. This is not an exact method.
It's exact, it's numerically exact as far the interval of time is small enough.
Well, you are assuming some form of potential.
Pardon?
You are assuming some specific form for the potential.
You know the potential, because here is the interaction between the helium atoms. So this isn't to be anything. Could be an external potential indeed, but could be also the internal, the pair potential between the helium atoms. So at the end is that measure of the energy what you use to create or destroy. So at the end you expect that because it's a diffusion equation, you reach an asymptotic state there. And this asymptotic state should represent what is the ground state of the system. Okay, but I will not enter into the details here, because what I'm more interested in the DFT, where at the end we explode more. Well, results with the quantum Monte Carlo, indeed we were getting right energies, and this is the histogram of these Walkers at the end of the day that represent the droplets. This is the radius, this is the density of the droplet, so at the end indeed we found that the surface is smooth, so it smoothly goes to zero. It creates some solvation cells, but it has pros and cons at the end. This method. The pros is that it's based on first principles. Okay, we are solving a Schrodinger equation and it's numerically exact in that sense. Yeah, indeed it is. Maybe I was not using the best representation of the equation, but indeed it is. But the problem is it scales really wrongly with the number of particles, because it's exponential scaling with the degrees of freedom. So the experimental droplets are in the size of thousands. We are talking here in the biggest droplet we compute is in the order of hundreds. So no way, no comparison with the experiments. Also, we cannot do dynamics, real-time dynamics with this method. This is out of the game. So at the end, what we decide is to move to density function. It's empirical. It's another philosophy. Here, you only work with a density that is the one that represents the system. And you start with the Hohenberg-Kohn theorem here, assuming that the energy is a functional of this density, of this one body density. This density is normalized to the number of particles, and it represents the shape of the droplet. So once you have this functional, you apply a variational principle. You fix some constraints, for instance, the total number of particles of your system, and then you make variations in order to get which is the density that minimizes the energy. With that, you get a Schrodinger-like equations for the many-body system that indeed gives you the ground state of the system, but the problem is the exact shape of this functional. That's something, by the theorem, we know that exists, but we don't know the form. So at the end, you need to use empirical guesses. After many years, we found a potential, a DFT functional that is able to reproduce more or most of the main properties of the helium. But this is fully empirical, so we add every term according to the particular effect we want to include. So we have a term for the kinetic energy, we have a term for the Lennard-Jones interactions. Without the core, we have a term that represents the short range interaction. We have corrections for the kinetic energy. We have the effect of the backflow, effect of helium, and also the solid transition if you have like high pressures in order to define the solidification of the fluid. So the philosophy is that it's fully empirical. This is assuming that, okay, even if I know from first principles how to solve the system, numerically it's impossible, because I cannot solve the Schrodinger equation when I have 1000 degrees of freedom. This is out of the game. So let's try to find a macroscopic description of the system that behaves as the original system. And I have to figure out from the empirical results that I have which is the particular shape of this. And I can tell you it works perfectly fine for the purpose of comparing with experiments. If we compare the profile with those obtained from first principles using diffusion Monte Carlo, the density fits really well, and it also represents quite correctly the elementary excitations of the helium. So now the idea is that once we have defined a function of a macroscopic description of the system that looks like it's able to represent the system, we want to really go beyond, compare with new experiments and doing real-time dynamics with that. So indeed, when we compare with experiments that you have the droplet and you have impurities and you excite this impurity could be any atom, could be calcium, could be silver, could be anything. You optically excite the atom and you measure the final velocity after the absorption of the atom from the droplet. And we compare the prediction from our method to the empirical results. And in that case, this represents the excitation energy to excite this atom and the final velocity distribution as a function of that energy. When the impurity is in the surface, we get something linear. The initial, the final kinetic energy of the atom is proportional to the initial excitation energy. But this changes a lot when you have the impurity inside the droplet, because in a superfluid you don't have viscosity until reaching a certain critical velocity. So in the experiment, what you observe if the impurity is inside the droplet is just a distribution of velocities that just end at this critical velocity. So that changes the picture as well of how is the diffusion of atoms inside superfluid. And that's a bit the point I want to go with this helium. So now the interesting part of these helium droplets is what happens if you put several elements into the same beam. Means that you have the droplet, you first dope the droplets with silver, for instance. You create a cluster of silver inside the droplets. Then you put gold, for instance, and then you have an extra layer of gold in this cluster of silver. So you can design nanoparticles using the helium droplets. The problem right now is that the structure of these clusters depends somehow in the initial conditions, but is not fully understood when you got a crystalline structure or multi-crystal or directly an aggregation fractal there. So, and that's the part that I would like to understand better and doing deeper into this, how this diffusion inside the superfluid environment works. Because indeed you have from 0 to the critical velocity that you don't have diffusion, then you have the diffusion, so it's when it works as a Walker. So in which conditions you can predict which is the particular structure that you will have inside. So we did some tests with that, simulating some clusters inside the helium droplets, and also using one of the atoms in order to learn which is the particular structure you have for this cluster. So you can experimentally use as a probe here a calcium atom in order to understand how the argon atoms are making a cluster around it. So by the optical excitations and the size of the shift or the width, you can predict which is this particular structure of that. So here we propose the experimental way to learn about the structure, and the simulations will tell us which initial conditions create which particular type of clusters or not. So why is important? Imagine that you combine in such a way these clusters that you have, for instance, calcium and oxygen, that they react. It's a quite energetic reaction. But in the middle you have argon. So you can create these nanoparticles with the two reagents there without acting with each other. But you have the argon in the middle that prevents the chemical reaction. So once you collect all these particles, you can activate the chemical reaction any moment you want with light. You just need to melt the argon layer in order to let the calcium and the oxygen to react together. And this is quite useful, for instance, for healthcare, in order to design drugs that they react in the very moment you decide, so that you can activate this reaction any moment, but also for defense, making control chemical reactions activated by light. I mean, it's in particular the Department of Defense in the United States that is interested in creating this type of new weapons, probably for the new wars. So, well, this is about superfluids. So what I wanted to tell you here is that indeed we have these two options, this microscopic description and microscopic description. So we need to learn how this diffusion occurs, happen inside these superfluid droplets, but also what happens if we use this philosophy or these computational techniques to other type of systems, and for instance, if we have people instead of molecules or atoms. So here is what it starts with the social physics. How we started working in that was in 2008 with the electoral results here in Spain. So we plot the number of votes, the logarithm of the number of votes with respect to the position of every party that year was in the elections. We could find some regularities there, a quite strong regularity, and the idea at that moment was that, okay, if you have a regularity, means that you can define a process that generates this regularity. So at that time, we understood the problem as a network where you grow cluster inside. And according to the conditions, you find particular distribution of sizes. And at that moment, that was kind of enough in order to classify these different distributions. It was not only for electoral results here, not only for Spain, but also in Italy, in UK, in the United States, but it also worked for population, for demographics. These are the rank plots of population of the cities of every of these provinces. So we took all the Spanish provinces, we ranked the cities, the municipalities according to population, and we found that the type of distribution was fitting those that we were creating in our networks. Okay, we had a system that was based on networks, that was about growing clustering inside these networks. It behaves as the empirical one, but we were not fully happy with that, because it doesn't mean that we have a theory. We have a system that behaves, a numerical system that behaves like the empirical one, but it doesn't need to have a theory. So we wanted to go deeper into that. So what we know is that the cities have been described as random walkers as well, the population of the cities. And following Gibras law of proportional growth. Basically tells you that the change in the population of the city for a particular year is something proportional to the own population. It means that the fluctuations indeed that bigger in bigger cities and are smaller in smaller cities. So in the week we checked that, and we had a question here. So first, this is, if you simulate proportional growth with walkers, you have geometrical random walkers. It means that if you change the variable to the logarithm of the population, you can linearize the equation. So you just get linear random walkers as usual. And we know that this system has been used for long to simulate the population of cities. Now, this is the question. We know that the random walkers are useful to simulate thermodynamics. It's a thermodynamic system. When you have an ensemble of walkers, they obey the principle of maximum entropy. So, if walkers are a correct description of population of cities, the natural question is to ask if the population of cities also obeys thermodynamics. Yep.
You assume that the cities are independent of each other.
Here, yes. So it would be equivalent to an ideal gas. But what is important is the constraints that you put here. So the idea is, let's simulate the cities as random walkers, independent, but we are gonna include two constraints here, in particular that the number of cities is fixed, and that the total population is fixed. So it's actually a problem of, you have a number of balls, a number of boxes, but in addition you know that the growth, the dynamics should be proportional growth. The question was, this is enough in order to predict what is the most probable distribution of population? And indeed it was. So that's basically enough to represent most of the distributions in the Spanish provinces. We went one by one, we were checking the dynamics you have there and comparing the distribution with that predicted by the maximum entropy principle. Maximum entropy just tells you which is the most probable distribution given some constraints. And indeed, when we were including these constraints, we were getting a really good match of the empirical distribution with the prediction. And you can see here how it works. This is really similar to what we were doing with the DFT. So with DFT, we have a principle that in that case was a Schrodinger equation. Here is the maximum entropy one. And we add terms, empirical terms, just because we know that this system behaves in that way. That those are constraints you include into your system. So as more information you have about the system, the better it's going to be the predictions. But sometimes only few of these constraints are enough to describe most of the system. And that was the case with the Spanish provinces here. So,
and so each city has its own Lagrange multiplier, or?
No, this is the wall. So here, this P is the distribution of sizes.
But you have two parameters, right? This mu and lambda.
Yeah, this mu is related with the number of particles, so it can be understood as a chemical potential in that sense. And this one is a kind of pressure. But the trick here is that the natural variable you should use is the logarithm of the population, not the population itself. That's the way you include the fact that you are dealing with proportional growth. So here, the constraint is that the total population is fixed. But I have to use the exponential of the logarithm to represent that the sum over all the cities is the total population of that particular province. So at the end, yeah, at the end is that you know the total population of a region, you know how many cities they are, so how they are distributed if you have proportional growth. That's basically the concept.
I'm a little bit confused. P of U is the actual density of people.
This is the distribution, this is the number of cities with a particular population.
The number of cities with a particular population.
Exactly.
Now, in that plot there, you have the population dependent with the distance, I guess, to the center of the city.
Yeah, no, this is the rank, and this is the population.
The rank of the
So you take every
So you
city.
take all cities. Sorry, I thought that was distance.
Yeah, no, sorry. Actually, this distribution here and the rank plot are related. So you can define the rank plot from the density, because you take the cumulative and then you inverse the cumulative and you get the rank plot. So predicting this is equivalent to predict this. But indeed, yeah, here is the rank. So Avila has like 200 municipalities, and this is the population of each of them. So
the populations are, the distributions are exponential.
yeah, at the end you have to work with the logarithm scale, because it's the natural thing. So the natural variable of a system, you can have an equation of motion that could be really complicated. And then if you are able to find the variable that linearizes the equation of motion, you have to apply the maximum entropy principle for this variable, not the original one, not the one that is the observable, but the one who linearizes the equation. That's all the trick here. Yeah.
Okay. Gibran law is designed to explain these distributions. You have the constraint, you explain better how the distribution deviates from the zip law for local areas.
Yeah, Zipf's law is a different constraint. So at the end, in Zipf's law, in order to get Zipf's law, you don't need to assume that the number of cities is constant.
You have infinite number of cities.
Yeah, because actually you find Zipf's law when you talk about urban areas and so on. No? So actually it's not that you have an entity, the entity is not well defined. But we have a paper in how to get the Zipf's law as well.
Not hips, the zips.
Zipf's law. Yeah.
It's just, it was already out there. Like the fact that this could be explained by the Gibran model is geography. What you added here?
Yeah, it could be an arbitrary point that is why to use provinces. Maybe there are other natural ways to define a particular region. But indeed, if we extend too much, the conditions at the end are quite different from one extreme to another. So indeed, there is kind of a size, a natural size, in order to define a region that actually that ends later. Okay. Yeah, that because you were asking, this is the non-interactive system, yeah. But indeed cities interact. Okay. Yeah, and that these typical distances at the end what defines you, which is the natural length or the surface that you should consider in order to assume that it's a coherent system. So, well, it got kind of viral at the moment, and that was also the motivation when we could make this link about thermodynamics and social systems is when we got the idea in order to create a company and make predictions about that, because that was at the level of the demography, but we can talk about this also about mobility, because that was kind of the idea. Here I was describing as a macroscopic, but now I wanted to describe it microscopically. I mean, here we were talking about how many people is in a city, but now I want to learn person by person, microscopically, how they move and where they go. And probably you know already about gravity model. This is
Sorry for the interruption. I mean, you show us a map for each province. Do you have the similar map for Thai Spain or Europe?
Yeah, indeed, but it doesn't fit. Because you are mixing systems. I mean, what is the limit that you consider that this is your system? They are not isolated systems at all. And here somehow I'm assuming that they are. So I should to consider a size where I can assume that they are under the same conditions. Because if you think about that as a thermodynamic system, you have variables at the end that are the thermodynamics parameter here. No? You can have a different temperature, you can have different pressure, so even the air in this room is changing locally. So if you want to really use a model that is based in ideal gas, you should consider a region where more or less all the elements of this system are under the same conditions. So if I put all the cities of Europe, actually it changes a lot. I mean, and at the end what you get, if you can see here, even between provinces there are some differences. Because, yeah, constraints, the value of these constraints are kind of different. So if we put it together, it's like if you are mixing systems with different temperature, different pressure, and so on.
So you have reached the local equilibrium and not global equilibrium?
Yeah, but pardon?
You are reaching local equilibrium.
Yeah, so
not global.
Yeah, no, global
What
no.
do you mean?
No, because at the end there is a correlation distance in this system, and that tells you how far you can go. But it's one of the next things I will show. There is correlation between the cities, that means that they are interacting. So it's not, but this interaction, since it's local, at this scale you might consider that it's almost gas, ideal gas. But these interactions are there, and they are important actually. But I will go to that later. So, well, in order to describe microscopical, so that was the idea of the company. So going to mobile operators, analyzing data from mobile phones, metadata, we don't see the conversations or things like that. What we have are which antenna someone is connecting and which is the antenna with the other one is connected and well. So with that we started to analyze mobility. Indeed we find patterns there. For instance, this is taking the center of Madrid, and we can see that actually most of the people doesn't move farther than 10 kilometers. So in your everyday business, and even in a month, it's not that you go really far from that. Then you have a small peak, that is the people who is doing long distances indeed. So at the end, somehow, here is telling us that it should be a spatial correlation already. Because at the end you have people that is going from one point to another, so that should create some kind of correlation. So, and when we study these long distance travels, we find a pattern that is very similar to that one that I showed you before, no, about the roads. Indeed, at the end, how people move as this supposed to be running water along the geography is not a two-dimensional system, homogeneous, not at all. So you definitely have something that behaves as a fractal, and the people is moving at the end inside a fractal. And that's a quite particular and interesting property of this mobility. So at the end, this how to explain this gravity model, these dependencies of the long-term distribution. So here we have a diffusion. When we talk about diffusion of people, it's not like the diffusion of the random walkers itself, because we find these long tail correlations there. But if we assume indeed a non-local version of Fick's law, we can reach this expression that goes as the 1 over the square of the distance for the kernel of the diffusion. So somehow, in order to describe the diffusion of people, we don't use a kernel that is Gaussian, but a kernel that is a Lorentzian. And that can be understood because of this long term. You don't have just people coming from the next layer close to you, but you can find people. The probability of finding people that is coming from really far is quite high. Just considering that, we have anomalous diffusion here that predicts the kernel for the human diffusion. So at the end, with this concept, what we did in the company is to define propagators. So if we have an estimation of which is the kernel of the diffusion and which are the patterns of, which is the geometry of the system where this diffusion is happening, we can define these propagators. At the end is telling you how 2 points are connected because the people that you can find in one point and in another. And at the end, we use this data to create these propagators, and it's what we are using basically for doing marketing campaigns. It can be used for many other purposes, but as a company where we found the fastest response from the market was for marketing campaigns. And in particular, we have been using it for the general elections in order to tell one party where they should put the people in the street in order to improve their results. We have been using it with United Nations as well for the refugee agency. These guys that sometimes you might see in the train station that try to make you donor for the refugees. They have this app where we tell them where they should go at what time, which particular day. So with that, they can organize the full team and improve their results. We have been working, we are negotiating with Red Cross now, with SThAR, Centro de Investigaciones Sociológicas. They also find useful this type of tool. With SThAR, we are negotiating with them where they should put the cars in order to get visibility. Probably you have seen these cars that are in the airport, no, right? Because there is a lot of people going in the airport, but probably you can get more visibility just parking some cars in the street in specific locations. So that's what we are doing for them. But it's not only that marketing, all the application. So we were negotiating with Global Dia also to make long-term predictions of how a particular highway is going to be used in the future. Since we have the models in order to simulate the growth of the cities, is what is our forecast of the use of a particular highway, this one in Galicia, for instance, depending on how the population of the different cities involved will change. So how the traffic in this highway is affected by the growth of population in Santander, for instance, and so on. So they can make this investment in the long term to learn if it's worth it or not to invest in a particular highway. This is the case with SThAR for mobility solutions as well. Get is a Uber-like app, no, that you can get a kind of taxi service, and indeed, which are the best places that the car should be close in order to increase the probability to find someone who wants a taxi in that particular moment. Also for healthcare, we can use these propagators in order to describe the propagation of a virus, for instance, for epidemics. And that's a project that we are doing we want to do with Médicos Sin Fronteras and Doctors Without Borders in Africa, in Ghana. We are negotiating there. And there is this one, also educational, that I like this one a lot. It's kind of make a video game in partnership with Transport Fever. That is they are in the video game industry. And we applied to a grant for National Geographic in order that the kids play SimCity-like games but learn about sustainability. So that at the end you make your city with the current laws of how the people is moving inside the city and how it should be in order to be sustainable. But let's go back again to this microscopic description about the cities, and we were saying about the interaction.
You say the people diffuse?
The probability to find someone. Yeah.
The way to find someone diffuse. Okay.
Yeah. With this data happen, you have data, but it's not fully exhaustive. So you just learn information about someone like spots of it. It's not a continuous trajectory. So you have somehow to figure out, which is from the last information you have about this person, which is the probability to find him anywhere else as a function of the time, until you have the next data set of this guy. Imagine this bubble chamber.
The safest bet is home.
Depending at what time and whom. Yeah. Yeah. But yeah, no, most of the people they are basically at home and at their workplace. Yeah. But for us, it's interesting which other places they visit in order to learn more about them and making segmentation. So if you are Red Bull and you are interested in young sportive people, how we can forecast or predict or estimate who of all these people is a young sportive person. So that's why we are interested in this, not only 2 places, 2 points correlations, but 3 and 4. That is someone who is visiting several. Everything is anonymized. And at the end we make aggregations of that, so privacy is conserved in that sense. But indeed, in a bubble chamber, for instance, you have information about the location of the particle every time you have a bubble. But you don't have a continuous set of bubbles, no? It's like discrete. So you have to figure out what happened in between, and which is the particular path that this person has taken. And that's where we use this diffusion in terms of the probability of finding these people. Then we aggregate over there all the people, and that's the probability of finding.
Okay, like when other people would do like a sort of Markov chain with the information of other people, you just assume that they go randomly along.
Not randomly, because then at the end you infer in which location they have been earlier. So, no?
Okay.
So you put all this information together in order to estimate these constraints that I was talking before. So for a particular person that at the end they don't move any random direction, right? So you have some guesses on where this person should be. So now it's the weekend, you don't know where he is, this guy, you know that the last weekend was in a particular city, so probably he will be there again. It's not 100% of prediction indeed, because...
Are you sure that what the diffusion is correct?
It's the diffusion of the probability itself. What diffuse there is the probability. Pardon?
I'm not sure I understand what it means.
The probability of finding that particular person, so imagine the case of the roads. So you are the police, and you see a car, and you get the number of the plate, and you lost the guy. No? So which is the probability to find this guy? If it's just 5 seconds later, this probability is going to be peak just in the place you see him last time. If it's 1 hour, probably it's going to be more diffuse. That's what I mean with the diffusion of the probability.
Broadening of it.
Yeah, exactly. But if you know something about this guy, that probably he was visiting his mother, then, and you know where his mother lives, you can put this constraint so it's not going to be any direction of the diffusion.
But when you analyze the movement of the people, in which place is you put the fact that there is different transportation ways? I mean, is this diffusion? I mean, the same if you are walking, if you take a car, if you take a plane.
No, definitely not.
So when you said I don't know, you put these models and you try to predict that, where on these models you put the transportation?
Yeah, because we filter that. I mean, we try to figure out who is going. For us, we are interested in the people who is walking.
Okay, so you take out of your data, you restrict to the line of people
that we think, because of the filter we have, that they should be walking. But at the end, we know that this is not perfect because it's really hard, and we know other groups that are working on that. But if indeed someone is following the highway, we don't even consider this guy for that particular thing. And that's particularly useful when you have an antenna that is covering the highway, but is also covering a residential place. So those that we detect that at the end they were just passing through.
Those trips are not considered for analysis.
Exactly.
Because the of people walking, and then you determine what are the typical paths of the people.
Yeah, exactly.
You have to have the people.
Because who is the promoter who is in the street, at the end they need to approach them in person. And in a time that they are not busy taking the bus or things like that. So at the end, that's the type of things that we filter. But for the application for the highways, it's the contrary. We are looking for those that are, so we take the other set of data in order to analyze the traffic of the highway. That indeed is not perfect. I'm probably sure that Google has much better data on that. All the people using Google Maps, and it's GPS, not antenna. But indeed, most of the effort for us is filling the holes of this data for using these CDRs. Because in the cities, you might have a resolution that is okay, probably it's just 50 or 100 meters, sometimes 50 meters, let's say. But in the middle of nowhere, the cells are huge. And you might have like 3 towns in the same cell. So in those cases, these people just go to the center of the town, and it works in order to differentiate if going to this town or this other town instead, more than defining a particular place.
Okay.
Yeah. So yeah, that was. So here I wanted to show these differences between macroscopic view, as we were doing with the cities, with the demographics, and a microscopic view, as we were doing with the trajectories. I'm going back to the macroscopic here because I want to introduce these correlations between the cities and what they mean. So something that I test after doing this ideal gas-like study is really check which is the correlation between these walkers, between these cities. And it's not only that there exists a correlation that depends on the distance. So I'm taking the trajectory somehow, that is at the end the demographic evolution of a city. I take the demographic evolution of the other city, the change in time of that, so the growth rates at the end, and the correlation depends on the distance, and decays. It decays with the distance. So at the end here in Spain, you have a typical distance that is around 80 kilometers. So that's what tells us more or less what we mean with a coherent system, that they should be more or less in the same thermodynamical conditions. Something that is a radius of 80 kilometers, more or less. But not only that, the system has memory. So the growth rates this year also are correlated with the growth rate last year, and this can go up to an average, the average time of 15 years actually. So it's quite a long-term memory here. So, okay, now how to introduce these effects into the equations of the walkers we have. So the trick is a Langevin equation. So because of the memory, that means that we have inertia, and because the interaction, because of the correlations, we have interaction. So we can expand these equations of the walkers, but now changing this assumption that they were gas-free, ideal gas. But now, indeed, we work with correlation between the forces and a factor here, a damping factor, just as Langevin equation. So at the end, we have in the beginning a set of equations that are linked between each other because this correlation. So we can think in the way of linearize these equations to uncouple the equations. So if we define this transformation, that at the end those are the eigenvectors of the correlation matrix, we decouple the equations. So at the end we have a set of n equations that represent collective modes of the system that are uncoupled. But what they really mean, so we did this numerical experiment here. So we have Spain, real data, we have Spain with random distribution of cities, we have Spain with a kind of regular distribution of cities. And we wanted to check which is these eigenmodes or eigenvectors that we get in order to uncouple the dynamic equations. And that was surprising. I mean, when we have, if we imagine a regular grid of cities, these collective modes that uncouple the equations at the end is something that looks pretty much to orbitals, no? Or the solution of the two-dimensional wave equation. And if we study the amplitudes of these modes and how they contribute to the total population, to the total dynamics, indeed we see that some modes are contributing more than others. So in these simulations, that is just following the equations we wrote, there is one mode that is the most important and the rest is kind of noisy. If we go to the real data, so this is 100 years of demographic evolution in Spain. If we describe this evolution not by the evolution of every municipality, like the population of every municipality, by describing by these eigenmodes that came from the diagonalization of the correlation matrix, we have this. There are actually two main modes that contribute to the total dynamics, and the rest that are basically noise. And what was interesting is that memory we detect, this inertia we detect in the data, is actually condensed in these two modes. The rest of the modes, this amplitude is completely random. They don't have memory.
What is the difference between top, middle, and bottom?
Those are three different states. So those are the components of these eigenvectors here. So the color represents how much a particular city is contributing to that mode. So here, for instance, this contribution that was done just using the walkers here means that those in the middle are contributing more than those in the outside. But when we go to the empirical one, so the ground state, or the main mode, that one with the highest eigenvalue that has a function of effective mass, actually. So we find positive what is around Madrid and the coast here, and negative what is Galicia and Andalusia. This is represented in the last 100 years, the migration from this part to this other part of Spain. And here, this other mode, we have the center of Madrid and probably Galicia and so on, so actually I don't fully understand this one. But this is representing another important collective mode in the evolution of the demographics in Spain.
Is it like orthogonal to the previous one?
Exactly. They are orthonormal. But this one that is already the 12 actually is completely kind of noisy.
In what sense this is similar to related to principle law in the composition?
Yeah, it's quite similar indeed. It's quite similar. But here I would say that the difference is that I have the equations that are Langevin-like, so we can make kind of the connection with the dynamics of physics.
Yeah,
and
but
so on.
what you are doing here is diagonalizing a correlation matrix
Exactly.
that you have evaluated from real data.
Yeah.
So
Exactly.
the fact that this correlation matrix is used for a Langevin equation or not is not relevant for this plot.
Yeah, but the advantage here is that if I want to make predictions about the population, since I know just these two modes, I have the equations. I know that I only
understand,
make...
but to do this plots, to decide if one mode, two modes, or 20 modes
This is
are the ones that
empirical.
are relevant, or the shape of the modes,
It's
or
empirical.
whatever, is empirical without, and in this is not used because what you match with the real data is the correlations, not the outcome of the stochastic model.
Exactly.
It's just the correlations to determine what are the correlations that you put in the model.
Exactly. Yeah. So here, in these simulations, I was using this homogeneous correlation that only depends on the distance.
Well, this is not simulation, this is the diagonalization of an eigenvalue, of a correlation matrix which is fully random.
Yeah, exactly.
You
Yeah.
are not numerically integrating anything to them.
Yeah. Well, I have here for the simulations, I was applying the same method I was using for the real data in order to compare. So I was having Welkers evolving and then diagonalizing and using the same process in order to see. But actually, there was something that is missing. Here, I was just assuming this correlation that only depends on the distance and that the population is growing with the years. And indeed, just with that, I cannot predict that exists two different modes there. I can only predict one mode. That is the one related with the total growth of the missing is probably the fact that you have migration from small towns to big cities. That at the end, urban areas are growing in a different rate as the smaller cities there. And this is a mechanism that I have not included there. And also that this correlation probably does not depend only on the distance, but also depending on where you are, will be more correlated with one place or another. That is not completely homogeneous. But those led me to find which is the difference, for instance, and which particular mechanism I should check in order to observe it in the empirical data. But here the advantage is that, for instance, I just need to make predictions about these two modes, and probably I have 90% of the contribution of the population of all the cities. Instead of worrying about making a prediction of 8,000 different municipalities, with only these two series here, this time series here, I can predict almost 20% of the demographic evolution. That's the main advantage of that. But also for me a question is that, yeah, so how far we can go with these collective modes? If we can even define kind of a technology of that. Because can we activate these modes? I mean, it works like in physics. Can you make some forces, apply these forces in some particular points in order to activate one mode in particular and not the other? And how it really works, no? These eigen modes represent a linear combination of the contribution of several places. So somehow we all are participating into that, but not independently. There are many things I would like to understand from this description here. So, yeah, summary of this part. Indeed, we can describe human mobility with the concept of propagators, taking this from physics, and it looks like works perfectly fine. At the macroscopic level, we can define a thermodynamics, not only ideal gas, but going a bit beyond and include these correlations and memories. I'm using Langevin equation. But indeed, there is something that is still missing. That is how far we can go with these collective modes and what they really mean, right? So now, as provised, so you see that
there have been many questions, but
we should go fast.
yeah.
Yeah. Okay. Yeah. Sorry. So I was wondering what happens if I have a Gaussian distribution of cities. Which are the eigen modes that I get in this situation? And that's something that is very similar to the orbitals of the harmonic oscillator, of the quantum harmonic oscillator. So I wanted to understand if it's really related. So going back to the propagator, so let's write this in this other particular way. What happens if we describe the Schrodinger equation with the propagator using eigenstates? So at the end, if also in imaginary time, if we have a small enough interval of time, we can split the Hamiltonian into the kinetic part, that at the end is analytical. We know that it has this Gaussian shape, and then the exponential of the potential here. So we know in that case that if we have the wave function and the stationary state passing through the propagator, we have the same stationary state with the exponential of the eigenenergy here, right? So in this quantum Monte Carlo, we were writing the wave function as a distribution of points. But what happens if I do the contrary? What happens if I write the Boltzmann factor, the potential, as a distribution of points instead of the wave function? If I do that and I transform the interval into a numerical sum of grid points, let's say, at the end I get something that is actually a vector, that is the wave function, times the free propagator evaluated at the points where I have created the grid from the Boltzmann distribution here for the exponential of this potential, that this is the equivalent that if I have the harmonic oscillator, this is the Gaussian distribution of points I was using there. So I get the same vector times the eigenvalue that is the exponential of the So in vectoral notations means that I just have that. So if I build a grid that is the Boltzmann distribution of the potential that I have there, I use these grid points in order to evaluate the free propagator at these points. I generate a matrix, and this is telling me that if I diagonalize this matrix, I get the eigenvectors and the eigenenergies. And indeed it works perfectly fine. So for instance here, I have up to 5 bosons, 5 particles in a trap. So I define a grid that actually is following just the confined potential, the potential mode. And by diagonalizing this, the matrix that is the propagator, the free propagator, but evaluated at these grid points, I can get as many states as I desire for this system. And indeed, then I can use all these states to compute the melting of the crystal and many other properties. I will go fast. What is really useful is precisely fractals. I can solve the Schrodinger equation in any complex geometry. The only thing I needed to put the points where I have defined the potential. And by diagonalizing this, I get the full eigenstates, the full spectrum of the system. I don't need derivatives, I don't need Fourier transform, I don't need to define the boundary conditions. Just evaluating that, I got the states. So we use it for this fractal, has really particular and nice properties that maybe on the day, but indeed I can use any geometry, and it's super easy to implement. And it was fun to be inspired by these demographics and this diagonalization of the population of Spain in order to get this model for solving a Schrodinger equation. So the idea is to use it for DFT, for the He in porous media, and to understand the diffusion in this complex geometries as well. So, well, that is. I don't want you to.
very much, Alberto, for this stimulating talk. We've had a number of questions, but perhaps there are a few more. Okay, they've asked me to use the microphone.
I haven't understood how do you, in the case of the Langevin equations, how do you pass from coupled system to uncoupled system just by diagonalizing the correlation? I haven't got that.
So I have the equations here. Okay, so those are the equations for free Brownian workers. There is no correlation between them. So I just have the derivative in time of the position is just growth rate times this. I linearize by using the logarithm. So now what I do is to define the Langevin equation of that in the playing with the variable.
To what inertia?
Pardon?
To what inertia?
So I extend the Brownian workers to Langevin equation by including the inertia here. So the derivative in time of the position, let's say, is just this velocity, and the acceleration is a force minus the drag force here. These forces are the ones that are correlated. So this matrix here is actually the square of this matrix is the correlation matrix. So if you take this form, you put it into the force, you solve the equations, and you compute the correlations. At the end, you get exactly that. The square of this matrix is the correlation matrix. So if I diagonalize this matrix and I get and I define a new set of variables as the linear combination of this, when you introduce this into the equations, at the end you linearize that with a new set of forces here that they are uncorrelated. But what you gain here is a mass, an effective mass, a mass factor, and that determines the contribution or the relevance of a particular mode to the total movement. But at the end, these are linear combinations of the original variables. Yeah. I don't know if.
That you are inventing a new Langevin equation in which you have some forces that are constructed to have the same correlations as the data.
So for this simulation.
And you construct it linearly and with some relationship with the noise so that the correlations are correct. So you don't really know what are the exact forces, but at least this gives the correct correlation.
Yeah, exactly. So since I don't have a better guess, now I'm assuming that these forces are just random numbers. So that indeed, if I know something, as this migration from the small cities to the big cities, I can introduce that term as a force as well, acting into the system.
Yes.
I have a question about the center of mass motion. In density functional theory, you make reference to this theory in the helium droplets. If I remember well, in the Kohn theorem, you always assume the presence of an external field.
Yeah, for electrons you need that.
While in your helium, there is no external field. No?
Because
it's self-bound.
It's self-bound indeed, because you have a Lennard-Jones-like potential. So at the end, this small, even if it's a weak attractive force, at the end you get bound systems.
But how do you deal with the center of mass?
Again, if you start the minimization with a constant density, for instance, that you just wait to condensate it, you need to break the symmetry. So we used to start the minimization with something that is already spherical, that the center of mass is already defined, and just wait to get the right shape of it.
So you always keep the center of mass fixed?
Yeah, and it doesn't change during the minimization. It should not change.
And could this be related to these eigenmodes you find, like center of mass
for the cities?
Motion? Yes.
That's well, yeah, no, I didn't really think about that. Yeah, I don't know if momentum is conserved in these systems, for instance. No? That would be something interesting to check. Which other symmetries we can find it. Yeah. Huh?
Any other comment? Question? Well, if not, Alberto is going to be here today. So if anyone is interested in talking to him this afternoon, just stay around now and let me know so we can organize. So thanks, Alberto.
with